Today we're going to talk about conditional probability, which will then build into independence, which we'll then use to have a product rule, and then we're going to take all of this and build it up into Bayes' rule. So when we're talking about probability, sometimes we don't care about the probability for a population at large as much as we do for a subgroup. For example, rather than caring what the probability is that any given person will have a heart attack, we might get more information out of that by breaking it into some age group. So I might be more interested in what's the probability that a person will have a heart attack given that they're between 50 and 60 years old. When we're looking at probabilities like this, we're looking at conditional probabilities. So in my conditional probability example, I was interested in the probability that a person has a heart attack given that they're between 50 and 60 years old. So I'm interested in the probability of my event B that I have here, the person has a heart attack, given my event A, the person is between 50 and 60 years old. So that's the words that I've been saying. So we're going to assign some notation to that. So my probability of B given A, we use a vertical line to denote given. And this is conditional probability. So remember, when taking any probability, I'm looking at a fraction where my numerator is my favorable outcomes and my denominator is my total outcomes. So in this case, I know that A is going to occur. And so my total possible outcomes is actually the probability of my event A. And the ones that are favorable to me are the ones where both B and A occur. My favorable outcomes is actually the probability of A and B, that intersection. Now notice the probability of A is my denominator, so I have to have the probability of A not being 0, so it has to be greater than 0. The next topic we're going to talk about is independence. When two events are independent, the outcome of the first one doesn't at all impact the outcome of the second one. So a standard example of this would be drawing cards from a deck of cards. So here I have a standard deck of cards, and I'm going to randomly pull a card out. So there we have it, the 4 of diamonds. All right, I've pulled the 4 of diamonds out. Now if I put the 4 of diamonds back into my deck of cards, I shuffle them around a little bit, and I go to pull a second card, I am just as likely to pull a 4, a diamond, a spade, a club, whatever, the second time. There we have a 9 of clubs, as I was the first time. Now, that's independent events. If instead I take my cards and I draw a random card out of it, 2 of clubs, and now I take my 2 of clubs and I set it off to the side. I don't put it back into the deck. So now the deck is, instead of a deck of 52 cards, it's a deck of 51 cards. There's only 3 2s left in the deck and only 12 clubs instead of 13. So the probability that I draw any card has been impacted because there's 1 fewer cards. There's only 51 cards in the deck. And my count of 2s is down, so the probability that I draw a 2 is smaller. The probability that I draw a club is smaller. And so when I draw the second card, the outcome of this actually depended on the outcome of the first. So that's an example of both independent and dependent events. So let's think about the first experiment we just did, drawing cards from a deck with replacing the cards back into the deck. So we're going to have event A, that the first card was a 4, and event B that the second card is a club. So when I think about the probability of these events, I'm going to think about the probability of B specifically for a minute. So the probability that I draw a second card as a club, again, remember my denominator is my total number of outcomes possible. There were 52 cards in the deck, and my numerator is favorable outcomes, so the card being a club is a favorable outcome, and there are 13 clubs in the deck. So the probability that the second card was a club was 1/4. Now, if I think about the probability of B given that A already happened, I drew a 4 as the first card. However, I put it back into the deck, so regardless of what that first card was, I still had 52 cards in the deck, regardless of what had happened with my first draw, and 13 of them were still clubs. So my probability of B given that A occurred was still 1/4. Whenever we have the probability of B equals the probability of B given A, or the probability of A equals the probability of A given B, then A and B are independent events. And this goes the other way too. If I know that A and B are independent events, then I can make these statements about the probability. So we actually write the words if and only if in here. And that means that if you know one, then the other one is true as well, and vice versa. Now, thinking about the second experiment that I just did, where I drew 2 cards without replacing the first one back into the deck, and I think about 2 events, the first one being the first card is a 2, and the second event B being the second card is a spade. So if I think about the probability of B completely without A, the probability that drawing a card from a deck that it's a spade, well, there are 52 cards in the deck, and 13 of them are spades. So the probability of B happening on its own is 1/4. Now, if I think about the probability of B given that A happened, so now when I drew a card from the deck and it was a 2 and I didn't replace it, my deck now has 51 cards in it instead of 52. And since it was a 2 of clubs, there are still 13 spades. So now I have a 13 out of 51 chance of drawing a spade. So notice now I have the probability of B is not equal to the probability of B given A. Right? Whenever this is the case, so whenever I don't satisfy my definition of independent, this means that A and B are dependent events. And it also could be that I see that probability of A is not equal to the probability of A given B. And if that's the case too, then A and B are dependent events. Now remember, our conditional probability for the probability of B given that A had occurred was the probability of A intersect B divided by the probability of A, provided that the probability of A was greater than 0. Whenever we talk about the product rule, or the multiplicative rule, really all we're doing is we're solving this equation for the probability of A intersect B. So to do that, all we do is we multiply both sides by the probability of A. And when we do that, we'll have the probability of A intersect B equals the probability of B given A times the probability of A, provided the probability of A is greater than 0. So sometimes we write it that it's the probability of A intersect B equals the probability of A times the probability of B given A. Again, provided that the probability of A is greater than 0. And again, this is just that the order doesn't matter when we multiply, right? So another version of this, remember, for independent events, A and B, the probability of B given A equals the probability of B. So for independent events, our product rule or multiplicative rule is going to look like the probability of A intersect B equals the probability of A. And instead of needing to write the probability of B given A, we can substitute in probability of B. So we can use this product rule for two independent events. In addition to having a specific product rule that works for independent events, we can also extend the product rule so that it works for more than 2 events. So let's consider 3 events, A, B, and C, that I want to know the probability of their intersection. So I can take them and I can think about them as being grouped together. So I'm going to think about A intersect B grouped together separate from C. So now when I take this probability, it's going to equal the probability of A intersect B times the probability of C given that A intersect B has occurred. And now I can take a look and I can use my product rule as it normally was for just 2 events to figure out what the probability of A intersect B was. And when I do that, I get the probability of A times the probability of B given A. And then I still have the times the probability of C given that A intersect B has occurred. So we can actually do this for however many. It doesn't just have to be 3. So I can actually generalize this, and instead of using A, B, and C, I could have been using subscripts to make it A1, A2, and A3, which will allow us to see if A1, the probability of A1 times the probability of A2 given A1, and the probability of A3 given A1 intersect A2, and so on. So if I wanted to generalize this, then what I have is the probability of A1 intersect A2 intersect, and I can keep on going with these intersections up to, say, AK. And this is going to equal the probability of A1 times the probability of A2 given A1 times the probability of A3 given A1 intersect A2. And we'll just keep on going with this until we have the probability of AK given A1 intersect A2 intersect all the way up to the intersection with A sub k minus 1. And just like the original product rule, my extended product rule also has a special case. So if A1 all the way up to AK are independent, then I have my probability of A1 intersect A2 intersect up to AK is going to equal the probability of A1 times the probability, now the probability of A2 given A1 when A1 and A2 were independent was just the probability of A2. And the probability of A3 given A1 and A2 when all three are independent is the probability of A3. And so on until I get to the probability of AK. A time where you'll see the product rule extended applied is when we have something that's analogous to drawing cards from a deck without replacement. So say we're drawing 4 cards from the deck instead of the 2 that we were, and we aren't replacing them along the way. Then we can use the product rule extended to figure out the probability that all of our events occur, and we draw all of the cards that we were looking for. There are times in the real world where we don't necessarily know the probability of an event that we need to know the probability for, or we don't necessarily know the conditional probability the right direction. So I don't necessarily know the probability of B given A, but I do know the probability of A given B for whatever reason. So the stuff we're going to do right now, ultimately ending up with Bayes' rule, is going to help us deal with the messiness of life as we encounter it with probability. So when we're talking about total probability, we need to think about our sample space as a partitioned set of outcomes. So in a partition, it's broken up into pieces like my B1, B2, B3, B4, B5 here. And each one of those pieces, each one of those sets of outcomes is not the empty set, which has the side effect that the probability of B sub I, for any of my BI's does not equal 0. Furthermore, there's no outcome that falls into 2 of my spaces. So BI intersect BJ for all I and j from 1 to k does equal the empty set. So we're going to be able to use that to find the probability of A. So I have this set A of outcomes that I'm interested in the probability of, and I don't know the probability of them. So what I can do is I can take the sum from I equals 1 to k, this is our summation notation, of the probability of BI intersect A. And I can actually write this as the sum I equals 1 to k of the probability of BI times the probability of A given B sub I. So that's the equation that is my theorem of total probability. And of course, it has to satisfy this partition stuff. So we can write all of the partition stuff out, that if B1, B2, up to Bk constitute a partition of the sample space S such that the probability of Bi does not equal 0, I equal to 1, 2, all the way up to K. Then, for any event A of S, we have, well, that equation right there. So if the probability of A intersect B equals the probability of A times the probability of A given B, then the probability of B intersect A should be the probability of B times the probability of A given B. Just pattern matching, so the first thing in the intersection is the thing that's standing on its own, and the conditional probability included is flipped. However, A intersect B is actually the same set of outcomes as B intersect A. And since that's the case, then the probability of A intersect B equals the probability of B intersect A. So this actually tells me then that the probability of A times the probability of B given A equals the probability of B times the probability of A given B. I actually can write my conditional probability that I had before, my probability of B given A. I can solve for it here, and I end up getting the probability of B given A equals the probability of B times the probability of A given B over the probability of A. So what I've done is I can find one conditional probability. I don't actually have to know the probability of the intersection. I just have to know all the pieces to be able to find it. So I need to know the probability of A, the probability of B, and the opposite conditional from what I'm looking for. And this is exactly what Bayes' rule is letting us do. But this two-event version doesn't actually fully give us Bayes' rule. What Bayes' rule says is if events B1, B2, up to Bk constitute a partition of the sample space S such that the probability of B sub I is not equal to 0 for all I between 1 and K, then for any event A in S, and everything up to here should look familiar. It should look like what we were using for our theorem of total probability. The only thing that we add for Bayes' rule is the idea that the probability of A can't equal 0. So what Bayes' rule is going to let us do is find the probability of some B sub R given A. And if we do that, this is conditional probability, so this is going to tell us that this is the probability of B sub R intersect A over the probability of A. But we know by our theorem of total probability that the probability of A can be written differently. So this is really the probability of B sub R intersect A divided by the sum from I equals 1 to k of the probability of b sub I intersect A. And we know from the work that we just did that our intersection, the probability of our intersection, can actually be written as the probability of BR times the probability of A given B sub R. And also, using the product rule, I can rewrite the sum that's in my denominator as the sum from I equals 1 to k of the probability of BI times the probability of A given B sub I. So for all of this, the R that's in here can be any number from 1 to k. And that's what Bayes' rule tells us. We have this equation, and so whatever part of the probability we know, we can fill it in. So if we don't know the probability of A, but we know the probabilities of all of our B's and the conditional probabilities, then we can actually find out the conditional probability of B sub R given A. So here's an example of when we might use Bayes' rule. So we have a manufacturing firm that's employing 3 analytical plans for the design and development of a particular product. For cost reasons, all 3 are used at varying times. In fact, plans 1, 2, and 3 are used for 30%, 20%, and 50% of the products respectively. The defect rate is different for the 3 procedures as follows. We have the probability of defective given that plan 1 was used is 0.01. The probability that's defective given that plan 2 was used is 0.03. And the probability that it's defective given that plan 3 was used is 0.02. So if a random product was observed and found to be defective, which plan was most likely used and thus responsible? So immediately looking at the conditional probabilities, you might think that plan 2 is most likely responsible because its probability of being defective, given that it was used, is highest. However, plan 2 is only used 20% of the time, so it might not actually be generating the most defective products. So we're going to use Bayes' rule to find out what the probability that a defective product was. So notice in this, I've selected a defective product already, and I want to know what the probability that each plan, so plan sub 1, was used, given that I've selected a defective product. So Bayes' rule tells me that I can use all of these conditional probabilities that I have in order to figure out what this new conditional probability is. So by Bayes' rule, I have that the probability of plan 1 being used times the probability of the product being defective given that plan 1 was used, divided by my sum from I equals 1 to 3, because I have 3 different plans that I could be using, of the probabilities that each of the plans is being used times the probability that it's defective given that each of the plans is used, will give me the conditional probability I'm looking for. So I already have all of my conditional probabilities labeled for me. I now need to figure out what is the probability of using plan 1. If I look at this, it tells me that plan 1 is used 30% of the time. So the probability of plan 1 being used is 0.3. Similarly, the probability of using plan 2 is used 20% of the time. So this will be 0.2. And finally, the probability of plan 3 being used is going to be 50%, so 0.5. So if I write this out, I'm going to have the probability of plan 1 being used times the probability of defective given that plan 1 was used in my numerator. And in my denominator, I will have the probability that plan 1 was used times the probability of defective given that plan 1 was used. So that's plugging 1 in for I. And then my summation notation tells me I need to add. So I'm going to add to that, plugging 2 in for I, incrementing up by 1. So the probability that P2 was used times the probability that it was defective given that P2 was used, plus incrementing up by 1 on I gets me to 3, which will be my final element because that's what's on the top of my summation notation. So the probability of plan 3 being used times the probability of a defective product given that plan 3 was used. So I can plug in values now for each of these. So I find that I have the probability that plan 1 was used is 0.3 times the probability that it's defective given that plan 1 was used was 0.01. So that's my numerator. This is all going to be divided by the probability of plan 1 being used of 0.3 times the probability of defective given plan 1 was used of 0.1 plus the probability plan 2 was used, 0.2, times the probability that it was defective given that plan 2 was used, which is 0.03, plus the probability that plan 3 was used, which is 0.5, times the probability it was defective given that plan 3 was used, which was 0.02. Now when I do all of that multiplication, addition, and division, I end up arriving at the probability of P1 being used given that it was defective is going to equal 0.003 divided by 0.019, which is going to equal 0.15. So now we can move on to finding the probability that plan 2 was used given that it was defective. So now I can look at this, and I've actually done all of the work for my denominator for all of my plans because my denominator is not going to change. It's always going to be the sum over all of my values from 1 to 3 for all of my plans. So my denominator is actually going to stay the same. I actually know the probability of it being defective now. And the probability of it being defective is 0.019. So the only thing that's going to change is my numerator. So I'll be putting in place of what I had before. I'm looking for the probability of plan 2 being used times the probability that it was defective given that plan 2 was used. So my probability that plan 2 was used is 0.2. And my probability that it was defective given that plan 2 was used is 0.03. So when I multiply that out, I get 0.006 divided by 0.019, which is going to be 0.316. And then finally, I'm looking for the probability that plan 3 was used given that it was defective. So again, my denominator is going to remain the probability that it was defective of 0.019 0.19. My numerator, though, will become the probability that plan 3 was used times the probability that it was defective given that plan 3 was used. So the probability that plan 3 was used was 0.5, and the probability that it was defective given that plan 2 was used was 0.02. And my denominator again stays the same. So when I do this multiplication out, I get 0.010 over 0.019. So this is going to equal 0.526. So now I can look at this and I can say that given that it was defective, that the one that I drew, the one it most likely was plan 3. So a defective product was most likely generated by plan 3. And I can do this because I have all of these conditional probabilities now. That the probability that plan 1 was used given it was defective is 0.158. The probability that plan 2 was used given that it was defective is 0.316. And the probability that plan 3 was used given that it was defective is 0.526. So since the probability is highest that plan 3 was used given it is defective, then that is the one that we assign as the most likely culprit.